NASA just revealed SpaceX Starship's docking port, and it's not built the way any spacecraft has ever docked before, a 171-foot rocket, over 100 tons, docking exactly where its fuel tanks already sit. Get this wrong, and NASA's entire moon landing plan doesn't work. So how do you build a doorway through tanks that were never meant to have one? Stay with me. What SpaceX just showed us changes everything about how Starship works. Here's the first thing you need to understand. Spacecraft have been docking with each other since the 1960s. It's not new. The Space Shuttle did it. The Soyuz does it. SpaceX's own Crew Dragon does it with the International Space Station right now, today. So why is this one different? Why does NASA's own rendering of Orion connecting to Starship's nose count as one of the boldest engineering moves space has ever attempted? Because of what's already sitting right there. At the very tip of a normal, reusable Starship, there are two tanks, small ones compared to the giant main tanks that fuel the rocket during launch. They're called header tanks, and they hold liquid oxygen and liquid methane. Their job isn't to power the ascent. Their job is to survive re-entry. To picture it simply, when Starship falls back through the atmosphere and performs that dramatic belly flop maneuver everyone's seen in the test flight videos, the vehicle needs precise control over its balance and its remaining fuel. The header tanks make that possible. They sit at the nose specifically because that's where the center of mass needs to be during landing, which means the exact real estate a docking port needs is already occupied by hardware that keeps the entire rocket from crashing. That's the setup. Now, here's the tension. A docking system isn't a simple hatch. It needs a rigid ring structure, precision latches, airtight seals, and a clear tunnel wide enough for astronauts in bulky suits to physically climb through. All of that needs to live in the nose, in a straight line, with no obstructions. But the header tanks are sitting right there. So the question NASA and SpaceX have been quietly wrestling with for years is this. How do you cut a clean, safe, pressurized tunnel through a section of the rocket that was never designed to have one? For Artemis 3, the answer turns out to be almost anticlimactic. And that's worth sitting with for a second because it tells you something about how SpaceX thinks. The Starship flying this specific mission isn't meant to survive re-entry at all. It's an expendable version, built to do one job and then be discarded. No belly flop landing, no atmospheric survival, which means no need for a heat shield and no need for header tanks. Take away the reason the tanks exist, and the nose becomes an empty canvas. SpaceX can install the docking adapter, the crew tunnel, and all the supporting hardware without fighting for space against fuel systems that serve no purpose on this flight. It's a clever workaround, but it's also temporary. And that's where the engineering puzzle really begins. The problem that doesn't go away. Here's the part most coverage of this story skips entirely, and it's worth spelling out clearly because it's the actual long-term challenge NASA and SpaceX still haven't fully solved in public. Once Starship becomes what it's actually designed to be, a fully reusable vehicle that launches, lands, and flies again, the header tanks come back. They have to. There's no version of a reusable Starship that survives re-entry without them. So the question becomes permanent. Not how do we get through Artemis 3, but how do we build a nose that can dock with Orion and still land itself safely every single time for years? Two possible answers keep surfacing. The first is almost architectural in how creative it is. Instead of placing the header tanks directly in front of the docking tunnel, reshape them, wrap them around it. Picture a straight passageway running through the dead center of the nose, and instead of blocking that path, the oxygen and methane tanks form a ring around the outside of it, like a donut wrapped around a straw. On paper, this preserves almost everything. The docking port stays exactly where engineers want it, right at the tip. The tanks stay close to where they're needed for engine operations. The overall shape of Starship barely changes, but nothing about this is free. Toroidal tanks, ring-shaped tanks, are dramatically harder to manufacture than the simple cylinders and spheres rockets normally use. They have to hold cryogenic propellant, fuel chilled to hundreds of degrees below zero, under real pressure, while that fuel sloshes around unpredictably in microgravity. Now build an entirely new plumbing network to move that fuel reliably during a high-stakes landing burn, where a single hiccup in fuel flow could mean engine trouble seconds before touchdown. That's option one. Elegant on paper, brutal to actually engineer. Option 2 throws out elegance entirely and goes for simplicity instead. Just move the tanks, push them off to the side of the nose, or relocate them further down the vehicle behind wherever the docking adapter ends up. That leaves the center of the nose completely open. No wrapping, no donut shape, just a clean, conventional docking tunnel. Sounds easier, and in some ways, it is. Integration with NASA's docking requirements gets simpler. The manufacturing gets simpler. But there's a catch nobody talks about. Mass doesn't disappear just because you move it. You're talking about relocating several tons of cryogenic propellant. That shifts Starship's balance during the exact moment balance matters most: re-entry and landing. Every structural calculation has to be redone. New reinforcements, new plumbing routes. And depending on exactly where the tanks end up, you might lose usable interior volume you were counting on for cargo or crew systems. So which one wins? Nobody outside SpaceX knows yet, and honestly, that's a decision worth watching closely, because whichever path they choose will likely become the standard template for every future Starship variant that needs to dock with anything, not just Orion. Why not just dock on the side? At this point, you might be thinking of an obvious workaround. Why not skip the nose problem entirely? Dock Orion to the side of Starship instead, the way the old space shuttle rode alongside its external fuel tank. It's a reasonable question. It comes up constantly, and it completely falls apart the moment you look at what Starship actually has to do during later Artemis missions. Starting with Artemis 4, Starship doesn't just act as a lander sitting quietly in lunar orbit. It becomes a space tug. It has to physically push the combined Orion-Starship stack toward the moon using its own Raptor engines. For that kind of propulsion to work efficiently, the thrust needs to fire directly through the combined center of mass of both vehicles. Nose-to-nose docking does this naturally, almost automatically, because everything lines up in a straight column. Side mounting breaks that completely. Every single engine burn would generate a twisting force across the docking connection. Not a small one either. We're talking about forces potentially strong enough to exceed what the Raptor engine's gimbal system, the mechanism that steers the engines, can compensate for, or worse, forces strong enough to physically stress and damage the docking structure itself. And that's before you even factor in basic flight stability. Keeping two spacecraft of wildly different sizes stable together is already a hard problem. Mount one of them off-center and you introduce constant, uneven forces that make attitude control, the ability to keep the whole stack pointed the right direction, far harder to manage. So side docking might look clean in a fan-made illustration. In real engineering terms, it's close to a nightmare scenario, which is exactly why nose-to-nose docking isn't just the cleanest option on the table. It may be the only one that actually works for what Artemis needs Starship to do. The 24 hours that actually matter. Now here's where the story shifts from design theory to something much more immediate. The Artemis 3 demonstration in low Earth orbit isn't just about proving two spacecraft can physically connect. That part, honestly, is the easy part. The real test is whether they can operate as a single unified spacecraft for a full day. 24 hours, that's the window. Think about the size mismatch here for a second. Orion weighs roughly 27 metric tons. Starship, fully fueled or even partially fueled, weighs well over 100 tons and stands roughly 171 feet tall. Once the two are docked, you don't have two independent vehicles anymore. You have one deeply lopsided combined spacecraft, with Starship dominating almost every measurement that matters. That creates an immediate control problem. Orion's small thrusters were built to steer Orion, just Orion, alone. They were never designed to wrestle control of a vehicle several times its own size. So during this test, control has to hand off to Starship's much more powerful thruster system, letting the larger vehicle steer and stabilize the entire combined stack. But the part that should really grab your attention is what's happening behind the scenes, on the ground. This is one of the clearest opportunities for engineers to watch how Orion's flight computers and Starship's flight software actually talk to each other in space. Not in a simulator, not in a lab, in orbit, for real, with two systems built by two completely separate organizations that have never flown attached to each other before. No simulation, no matter how sophisticated, perfectly captures what happens when two independently developed spacecraft have to operate as one. That's not a small technical footnote. That's the actual heart of what this mission is testing. To push the connection further, NASA and SpaceX are expected to run a series of controlled attitude maneuvers, deliberately firing Starship's thrusters to put real, physical stress on the docking joint. This isn't an accident to be avoided. It's intentional. Engineers want to see, under actual flight conditions, exactly how much the combined structure flexes, how it responds, and whether that docking adapter is rigid enough to handle years of future deep space missions. Some analysts have gone further, suggesting the test could include a low-throttle Raptor engine firing after docking is complete, essentially Starship gently pushing Orion from behind. If that happens, it would be the first real data on how the docking connection handles sustained forward acceleration. NASA and SpaceX haven't confirmed this publicly, but if it's in the flight plan, it would answer questions that no ground test could ever fully replicate. Through all of this, the astronauts stay inside Orion. On this particular mission, Starship isn't playing the role of lunar lander. It's playing the role of structural pathfinder, essentially proving the connection works before anyone trusts it with an actual moon landing. And despite how dramatic all of this sounds, the maneuvers themselves are expected to stay gentle. Even during active attitude changes, acceleration is expected to stay well below half a G. Noticeable to the astronauts inside, sure, but controlled, deliberate, nothing close to violent. By the end of those 24 hours, NASA and SpaceX won't just know if the docking mechanism holds. They'll know something much bigger: whether two spacecraft, born from two completely different engineering cultures, can genuinely function as one unified vehicle. And that capability sits at the core of every single Artemis mission that comes after this one. The docking system that plays both roles. There's one detail in this whole story that deserves far more attention than it's getting, because it might end up being the most important engineering decision in the entire plan. Every docking system that's flown before follows the same basic rule. One spacecraft is the chaser, the active vehicle that does the maneuvering and initiates the connection. The other is the target, the passive vehicle that simply waits to be docked with. Crew Dragon works exactly this way. It's built as an active vehicle, and it can only connect to passive ports already installed on the International Space Station. Fixed roles, no flexibility. Starship appears to break that rule entirely. While its docking system is expected to remain compatible with the international docking standard everyone else uses, Starship is widely believed to use what's called an androgynous active-active design. In plain terms, every docking port carries both the active and the passive hardware built in at the same time. Either spacecraft can start the docking sequence. Either one can accept it. There's no permanently fixed role. That might sound like a small technical detail. It isn't. It quietly unlocks an entirely different way of running space operations. Think about orbital refueling. Under the old model, you'd need one docking design for tanker vehicles and a completely different one for fuel depots. Under this new model, every single Starship speaks the same docking language. A depot can receive one tanker after another without needing separate hardware for each role. And if mission conditions demand it, the depot itself could become the active vehicle and maneuver to dock with something else entirely. Now apply that same logic to something far more serious: rescue missions. If a crewed Starship or a lunar lander variant runs into a critical problem in Earth orbit or somewhere near the moon, a traditional docking system would force planners to figure out in advance exactly which vehicle needs to carry the active hardware and which one carries the passive hardware. That takes time you might not have in an emergency. An androgynous system removes that constraint completely. Any compatible Starship in the fleet could potentially perform the rescue, because either vehicle is capable of taking the active role. The mission planning gets dramatically simpler, because engineers stop worrying about which spacecraft has which hardware and start focusing purely on getting help there fast. For a transportation system that SpaceX wants flying constantly, to Earth orbit, to the moon, and eventually to Mars, that kind of interchangeability isn't a nice bonus feature. It might end up being one of the defining architectural decisions of the entire Starship program. So what does this actually mean? Step back from the individual engineering details for a second, and a clearer picture forms. This isn't really a story about a docking port, not at its core. It's a story about SpaceX being forced to solve a problem that has no established playbook. Every docking system that's ever flown was designed for spacecraft built around the assumption of docking from the start. Starship wasn't. Starship was designed first as a reusable rocket that needs to survive violent re-entry and landing, and only afterward asked to also become a spacecraft capable of docking with an entirely different vehicle built by an entirely different agency. That's why the header tank problem matters so much. It's not a minor design inconvenience. It's a direct collision between two competing requirements: survivability during landing and functionality during docking, that both need the exact same physical space at the exact same point on the vehicle. And the way SpaceX chooses to resolve that collision, whether through toroidal tanks or relocated tanks, will likely shape every future Starship variant that needs to connect with anything else in space. At the same time, the androgynous docking system tells you something about how SpaceX is thinking beyond just Artemis 3. They're not just solving today's docking problem. They're building infrastructure meant to support refueling depots, rescue operations, and a fleet of interchangeable vehicles that can adapt to situations nobody has fully mapped out yet. That leaves one real question on the table. Is NASA comfortable enough with this level of design flexibility to fully commit future Artemis missions to it? Or will pressure from a fixed 2027 timeline force some of these bigger, more elegant long-term solutions to get simplified or delayed? That answer isn't public yet, but the next 24-hour demonstration in low Earth orbit is going to tell us a lot more than just whether two spacecraft can connect. That's the engineering behind Starship's docking port. Thanks for watching. I'm Adrian, the Space Brief. Like, share, comment, subscribe, and check the video right there on screen now.